Hello everyone, my name is Amit Khan. In this presentation, I will discuss about control actions and process controllers. What is process control system? In process control, the term process is used in very general sense and applied to continuous process. Some definitions of the term process are: it is a series of actions or operations conducing to an end, or it is a course of operation, natural or artificial, or we can define a process as a systematic series of operations in production. Here we can see the block diagram of a process control system, which contains the reference input set point, then an error detector, then control elements, which inputs is an actuating signal, then the output of the control elements goes to the plant, which is manipulated variable. Then in the plant we get also disturbance. From plant a feedback path is sent. The feedback signal is sent to the error signal, and the control variable output is the output we get from the plant. What are the elements of a process control system? The process variables are input variables, output variables, control variables, manipulated variables, and disturbances. So input variables are classified as manipulated or disturbance. The disturbances are further classified as measured or unmeasured, and output variables classify as at measured or unmeasured variables. Now, input variables convey the effect of surroundings on the process, while output variables convey the effect of process on the surroundings. Manipulated variables are the ones which are chosen to affect the change in control variables. The particular variables to be controlled in control variable. The desired condition of the control variable is called the reference or set point. Disturbances are also known as load. It can be measurable or immeasurable. Now comes what are the roles of controllers in process industry. Basically, proportional integral derivative, that means PID controllers, are used in most automatic process control applications in industry to regulate flow, temperature, pressure, level, and many other industrial process variables. Temperature control is a typical application that all uses these three controllers. Then comes what is sequential and modulating control. A modulating control valve is an automated valve that is used to control the amount of flow in a system or process. But a sequential control is an event-based process in which one event follows another until the process sequence is complete. Then example of a single industrial control loop showing continuously modulated control of process flow. A control system in which the individual steps are processed in a predetermined order, progression from one sequence step to the next being dependent on defined condition being satisfied. Next comes controllers and control actions. A controller is the most important component of the control system. It is responsible for the performance of the control system. The controller receives the difference between the reference set point and the measured output, which is also known as error, and generates a control action to make the error 0. Now, what are the control actions? There are different types of control actions. First one is continuous control mode, which consists of PI, PID, PD. Control modes, that means proportional, integral, derivative, and composite modes are PI proportional integral, PD proportional derivative, and PID is proportional integral derivative mode. And there are also discontinuous control modes, which consist of two position mode, multi position mode, and floating control mode. Next comes what is on-off controllers. On-off control is the simplest form of feedback control. An on-off controller simply drives the manipulated variable from fully closed to fully open, depending on the position of the control variable relative to the set point. Its example is the domestic heating system. It is basically a two-position control. Next is what is neutral zone. It is also called as dead zone or differential gap. A dead band, dead zone or neutral zone is a band of input values in the domain of a transfer function in a control system or signal processing system where the output is 0. Next is what is proportional control. Proportional control is a type of linear feedback control system in which a correction is applied to the control variable which is proportional to the difference between the desired value and the measured value. Next is what is offset. Offset is a sustained error that cannot be eliminated by proportional control alone. Next is what is proportional band. The proportional band of a proportional controller is the range of input signals which will cause the output signal of the controller to vary over its whole working range. The proportional band of the controller will then be the range of deviation which causes the output signal to change from 3 to 15 psi. Then comes what is integral controller. Integral control is a control mode where the controller output is proportional to the integral of the error with respect to time. And in derivative controller, the derivative control is the reaction to the rate at which the error has been changing, and it slows the rate of change of the controller output. Next comes what is the uses of P, I and T controllers. The proportional mode tends to be used in process where the gain Kp can be made large enough to reduce the steady state error to an acceptable level. But the integral mode over proportional mode is used when we have to eliminate the steady state error, and the derivative control is used to reduce the magnitude of the overshoot produced by the integral component and to improve process stability. Now these are the equations of PI and D controllers. We can see the output of proportional controller is Kp into Et, and integral controller is Ki into integral 0 to t et dt, and for derivative control it is Kd into ddt of Et. E is the error signal, and Kp, Ki and Kd are the proportional, integral and derivative gains for proportional controller, integral controller and derivative controller respectively. Now what is Kp? Kp is the proportional gain between error and controller output. Ki is integral gain and Kd is derivative gain. So what is error? Error is set point minus control variable. Now if we compare P, I and D control modes, we get that P is the simplest controller to tune and offset with sustained disturbance or set point change. But Pi is more complicated to tune than P or proportional controller. It has better performance than proportional controller, but Pi means proportional integral controller has no offset. It is the main advantage of PI controller. And PID is the most complicated controller to tune, but it has the better performance than PI and obviously P controller, and it has also no offset. Next comes composite controllers. First one is PI controller, that is proportional integral controller. It is a feedback control loop that calculates an error signal by taking the difference between the output of a system, which in case is the power being drawn from the battery, and set point. Its governing equation is Kp into E plus Ki into integral Et dt. Kp is the proportional, Kp into E is the proportional part, then Ki into integral Et dt is the integral part. Same comes for PD controller, that is proportional derivative mode. The output or governing equation is Kp into E for proportional mode and plus Kd into ddt of Et, that is for derivative mode. And for PID controller, it is proportional plus integral plus derivative mode. It has a huge application in industrial control applications, like to regulate temperature, flow, pressure, speed and other process variable. Now here is a PID controller. The governing equation of a PID controller is Kp into E plus Ki integration Et dt plus Kd into ddt of Et. So the Kp into E is the proportional term, the Ki integral 0 to t Et dt is the integral term, and Kd into ddt of Et is the differential term. Now there is a comparison of PPI PID controllers. The parameters are given. When we increase K, that means proportional gain, the speed of response increases, stability deteriorates and accuracy improves. When we increase Ki, that means integral gain, the speed of response decreases, stability deteriorates and accuracy improves. Increasing Kd, that means derivative gain, the speed of response increases, stability improves and there is no impact in accuracy. Also we can see that there are different effects on various output parameters of PPI and PID controller with respect to variation in rise time. Here are the applications of different controllers, and here is a comparison also. We can see that P controller when to use when the system with slow response and the system can tolerate an offset, then we can use P controller. Examples are float valves, thermostats. Then I controller, it is not often used alone as it is very slow and it is used for very noisy systems. Then D means derivative controller, it is not used alone because it is too sensitive to noise and does not have set point. Then comes PI, it is very often used, that means proportional integral controller. Examples are thermostats, flow control, pressure control. This type of controls PI controller is used. Then comes PID controller, it is mostly used. PID controller is very often used in process industries. It is most robust but can be noise sensitive. Examples are cases where the system has inertia that could get out of hand. That means examples is temperature and concentration measurement on a reactor to avoid runaway. Here we can see in that another diagram that here are the closed loop step response of different controllers. That means closed loop step response of the system when we use P controller, PI controller and PID controller. Now here is the practical application of temperature control of an on-off controller. Suppose we have taken an example of temperature control of an industrial oven, and we have used an on-off controller. So based on the errors, the heating elements are turned on or off by the controller. There are no intermediate values of heating element, they are fully on or fully off. So as we can see that when activated, the controller will sense the temperature difference and it will be on or it will be off. As we can see, the on-off controller cannot keep a steady temperature in the oven but always goes above and below the set point. This cycling around the set point value is called hunting. As we can see in the image, when the error is positive, the controller is switched on, and when the error is 0 or negative, the controller output is set to off. This is a practical application of PPI PID controllers in PID temperature controller. You can see the block diagram. We have used here a PID controller which is consist of P, I and D controller. Here the proportional control makes a correction term proportional to the error. The integral control makes a correction term that integrates the error with respect to time, and the derivative control makes a correction term that differentiates the error with respect to time. Now in P controller, in the temperature control loop, the proportional controller designed to eliminate the cycling associated with on-off control. The proportional controller decreases the average power supply to the heater as the temperature approaches set point. So this has the effect of slowing down the heater so that it will not overshoot the set point but will approach the set point and maintain a stable temperature. This proportional action can be accomplished by turning the output on and off for short time intervals. Next is PI controller in the same temperature control loop. Due to the limitation of P controller, where there always exists an offset between the process variable and set point, I controller is needed. The integral controller provides necessary action to eliminate the steady state error. It integrates the error over a period of time until the error value reaches to 0. It holds the value to final control device at which error becomes 0. It decreases its output when negative error takes place. Here the speed of response can be increased by decreasing the integral gain Ki. Next is the PID controller in the same temperature control loop. The I controller doesn't have the capability to predict the future behavior of the error, so it reacts normally once the set point is changed. Now we have introduced D controller, that is derivative controller. It overcomes this problem by anticipating future behavior of the error. As derivative controller can anticipate the future behavior of the error, so its output depends on the rate of change of error with respect to time multiplied by derivative constant. It gives the kick start for the output, thereby increasing system response. Thank you all for watching and listening to this presentation.